But what does that relate to? Particles, which are formula units, molecules, and atoms. So if I give you moles of something and I say go to particles, that is what you have to do. That is the only conversion that will ever get you to particles. Do not make up random stuff. Okay? Random stuff does not. There are established relationships and you have to know them. But if you don't know them now, you will today because we're going to use them quite a bit. Okay, so we got particles and moles, and what else? Grams and moles. And how would you know the number of grams that a particular substance is worth in moles and grams? From PTOE. So all you're doing is grabbing PTOE, looking at the mass underneath the element, and adding it up appropriately according to the subscripts designated. And then the third one, so we have molar mass, we have represented particles, and volume. What is molar volume?
2.4.
What's the unit? Liters per 1 mole, right? Those are the three, and we're going to use them extensively today. So keep those in mind. Now talk to me through how you would approach the problem. I'm not going to write a lot of numbers down. I'm just going to write the process so we see the magic of canceling units again. Okay, so tell me, where do you start on this Connors group? Right, so you're starting with molecules. So on your guys' quest, some of you guys did not write the unit. This is all about units. I could give you hieroglyphics for the dang numbers and like say convert, but if you don't have the units, you have no idea what you're doing. So you're starting with number of molecules of what? CO2. And then the question is what, Brooks group?
The mass.
Okay, so grams, right? Looking for grams of CO2. It's nice to establish the question up front. That way it kind of gives you like a light at the end of the tunnel where you're going with this. So I can't do anything with molecules except convert to what, Kaylee? No.
Wait, what's your question?
I'm looking for how to convert from, if I have molecules, there's only one thing I can convert to. That's useful. Using Avogadro's to get to what then? Moles, right? I'm converting 2 moles and the conversion is using Avogadro's. So you would put 1 mole of CO2 on top and then molecules on bottom, but with molecules of CO2 you would put 6.022 times 10 to the 23rd. Okay, so then I'm in moles, which is great. Give me to grams, Ian. How would I get from moles to grams? Or Ian's group, because that's what you guys have talked about in groups. Together, forever, yeah. Where did you get the mass from? Right, so then you convert by canceling moles on bottom, so 1 mole of CO2 weighs, you guys calculate this in your head? 44. So carbon weighs plus oxygen plus another 16, 44. There we go. So that one actually, I am putting the number up here. Adding it up straight from PTOE. If I just told you you're doing test corrections because your grade was not fantastic, what am I doing right now? Giving you the answers to the quest. Make sure you're writing stuff down. Okay, so tell me how you would proceed through question 2. Take a minute to establish what you think. Courtney's group, tell me what you would start with.
For number 2, you would start with 553.0 grams of sodium carbonate.
So grams of sodium carbonate. What's the sodium carbonate's formula? Anybody?
Na2CO3.
Okay.
And then you multiply it by 1 mole on top.
Of sodium carbonate.
Yes.
And on bottom? Don't tell me the number. Just tell me what the process is.
Oh, you have to find how much the compound is.
So you'd say grams of sodium carbonate on bottom. So you'd find that straight from PTOE. So just put PTOE there. Okay, so then we have grams and grams canceling. Now we are stuck in moles. What do we want to get to here? Moles of sodium carbonate. Are we done? We're done. Okay. So this one I will start for you because this one's a little different actually from your quest. How many atoms of calcium? So question atoms of calcium is my question. That's really nice to write because if you forget to go back and read, you might get to atoms of something and not realize you're at the wrong answer. So how many atoms of calcium are in this much grams of calcium phosphide? What is calcium phosphide? C3P2. Calcium phosphide is just a binary one, not calcium phosphate, calcium phosphide. Okay, so then if I'm in grams of calcium phosphide and I want to eventually get to atoms, I cannot go straight from grams to atoms. There is no conversion for that. What do I have to convert from, to Connor and Lucas? Okay, so you just convert from grams to moles. Moles is the magical stepping stone, right? So 1 mole of calcium phosphide and moles on the, grams on the bottom would just be straight from the PTOE, so I'm going to put PTOE right there. Grams of calcium phosphide. Okay, now I'm in moles of calcium phosphide. What type of particle could I convert to right now, Zach? If this is an ionic compound. Particle. Grams is mass, right? What are the 3 particles? Atoms.
Molecule.
And yes, okay, so which of the 3 would apply here? Kira, which would apply here? Not of this whole thing here. What kind of compound is this? Anybody? Calcium phosphide, ionic or covalent? Okay, what term goes with ionic? Formula unit. So I'm going to go, I have a huge gram amount, I've narrowed it down to a mole of it. Now I'm going to break it down to just in a huge bowl of calcium phosphide, I take out one of those things, and those things are called formula units. So 1 mole on this side here. And then how many formula units are in a mole? A whole particle, right? The particle number 6.022 times 10 to the 23rd formula units of calcium phosphide. Okay, so now I have my big bowl. Now I pick out 1 formula unit. Look at it really closely. How many atoms of calcium are in that formula unit? And 1 formula unit, what does 1 formula unit look like? Looks like this. That is 1 formula unit. There are 3 atoms of calcium. Good. So 1 formula unit contains 3 atoms of oxygen. Calcium, yep, that one. Calcium. So that one went from grams to moles to formula units to 1 atom, or atoms from that formula unit. Okay, yeah. Ready for this one?
No.
You're gonna ask me a question?
Quick question. You did 3 atom calcium over 1 atom C3C2. Would you like to, instead of the changing it forming first, you did switch mole ratio and then?
So the internal mole ratio? Yes, you could. I'm just doing more conceptual to make sure people understand what a formula unit actually is. You could do it multiple ways. Okay, for this last one, what am I starting with, Arushi? Atoms, right? So I'm starting with atoms of neon. Get me to a usable unit, Kevin. You can't, so you know you cannot go straight from atoms to liters. There is no conversion whatsoever there. What's our stepping stone? Moles. How do I get to moles from atoms? Atoms on bottom and mole on top. So 1 mole of neon has how many atoms in it? Avogadro's number again. So you'll realize that anytime you see atoms, molecules, or formula units, you need to be using particle number, the Avogadro number. If I'm in moles of neon, which is a gas, get me to liters. Mike and Jamie's group. Come on. Okay, goes where? 22.4 liters on top and 1 mole on bottom. 1 mole of a gas. And so this is only true at STP only for a gas. So those are 2 numbers you must memorize. Avogadro's number, goes with particles, and 22.4 liters goes with molar volume. Other than that, are there any other molar conversions? Not really. But you just have to know which ones are direct relationships. So if there's like a multi-step process, you can go, okay, I can't go straight from atoms to liters. There's something in the middle, and that's moles usually. And then you can go from there. All right, who feels pretty good for the review of the quest now? Okay, so those of you who I'm going to ask, I have the 2 classes, sorry, I'll pass them out shortly. We are going to talk about that Wednesday. All right, so does this kind of represent what we just talked about, except for the whole Rabbittville thing? Yeah? I can start you off with volume of something, then immediately you go to moles. Then I would ask you to go to atoms of something. Well, you're in moles. How do you get to atoms? Avogadro's number. So there's these three relationships, but they can be mixed up in many different ways. Okay, I'm gonna leave that there for a second. I'll take questions on reading gut 12 now. Reading gut 12. Yeah.
Number 5.
Cinco. Let's see here. Why is it important that you cancel as you proceed through stoichiometry problems? Give me a general answer, anybody.
So that, like, it cancels those balances.
So yeah, so you're canceling, so it's balanced, but more along the lines you're making appropriate conversions. So if you can't cancel all your units at the end except for the one you desired, that means that you made an inappropriate step. That means that the conversion process was incorrect. It's about just making sure your conversions are correct.
Okay, yeah, that's what
If there's no more than that. Okay. Another question?
What is a mole ratio?
A mole ratio is from a balanced chemical equation. So good question. Hold on. This is a mole ratio. Hydrogen, there's this recipe to make water. This recipe calls for 2 moles of hydrogen gas and 1 mole of oxygen gas to make 2 moles of water. So the mole ratio is a 2 to 1, or a 2 to 2, or a 1 to 2, anything that's related to coefficients. It's about the recipe. So a mole ratio represents the recipe of a reaction. How many of each that you need? Another question from reading gut 12? Yay, nay? Yay? Ready?
Number 1, how do you determine the amount of moles in one compound?
You'd have to probably convert from grams of some sort, but moles generally, sometimes moles are given, but the other ones, like the atoms and molecules, oh no, this is in a chemical equation, not just in a compound. In a chemical equation, it's based off the coefficients again. So now I'll actually leave this here because this does relate to our question. So you can call these mole ratios here. Sometimes we call them molecule ratios because how are moles and molecules related? Everybody? Avogadro's number. So as long as they're all related by the same technique, so Avogadro's number, Avogadro's number, Avogadro's number, then sometimes you can call them molecule ratios or liter ratios because everything relates back to Avogadro's number.
Attention teachers, please allow the sophomores with the last names that begin L through Z to go to the cafeteria at this time for the planned re-administration, and they should bring their belongings with them. Thank you.
Okay, you're bringing your belongings with you. Pass up reading gut 12 right now. Pass up problem set 11 right now. Types of reaction lab. You guys think it's NIE lab? Sorry, never mind. We didn't get to that yesterday. Pass that up right now. And then my people who have to leave, adios. You guys will have a video. I'll have it on room video.
What do you say about type 2 reaction?
Pass up homework, pass up labs.
Cool.
And I want my 10th graders to leave now so that we can start the rest of class.
I will be until tomorrow, so I'll make all this up.
Morgan.
Do you have the lab card that we didn't use? Oh my gosh, yeah. No. I really know.
Alright, everything should be passed up, guys. Sophomores, watch the video. Rishi.
Wait, did you turn it on?
Yeah.
No.
It's the last in the box or the last in the stack. It's not on here. Do you want the stack? Sorry. What she did was perfect. I'll do this. Okay, all right. I know. I didn't get I just have it. Okay, guys. one scooch to an empty seat. The second one scooch to an empty seat. I don't think they're fine. I'm not sure. Okay, okay. The four of you sitting over there, scooch over here. I'm in business now because we're about to run a marathon, people. I hope you brought your marathon shoes.
Oh, my shorts are
Well, you're running barefoot, okay?
I'm not properly hydrated. Yeah, what happens if we pass out though?
I will save you. That is my job. Okay. Yeah. It's many slides back. There it is. Okay. So, here's what I'd like for you to do. Refocus. You got it? First step one is refocus. Step two, pull out the note sheet I gave you 2 days ago. It was 4-2 page. It has a big, huge flow map on it. Something similar to this, but that's more. If you don't have it, then I will find extras momentarily.
The one with like.
Yep. Can I hold this? Hold this up. It looks like this. Okay, so now you're probably realizing that I reviewed that initial stuff because the stuff we learned a week ago with composition stoichiometry, with moles, atoms, grams. We're going to start to pull that together with reactions now, because now we have another tool in our tool belt called reactions, and we're going to do reaction stoichiometry, which is just simply talking about reactants and products at the same time in the same problem versus separately. So that's why I want you to make sure you remember your reactions. You have your notes out from reactions if you need them. But other than that, I think that once I do 2 problems, I'm going to stop and say, tell me what you guys think. If you get it, I'm done. You guys are going to practice. If you don't, then I'm going to have some of us break off and do separate. Because I probably have a million questions I could do, and I'll do it all day long. You know I will, but I don't want to if I don't have to. I want you guys to let me know. Be vocal and participate. Because my last class, I told them, some of them were participating a lot. I told them I'd give them more money for their help with this. Yeah.
Is the foldable due
On test day.
okay.
Yeah, don't worry about that yet. Okay, so we're going to pull this together with reactions. So on that chart you have there, I'm going to scroll to it real fast. It's a couple slides back. Sorry about this. Maybe. Yeah, nope. There we go. Here. We have, we're going to talk about volume of solution at the end. We have particles, we have volume of gases, and we have mass. We all know how to get to moles of that particular item, right? This is moles of X, whatever X is. Let's call it a reactant. If I ever want you to go from moles of one thing to moles of a totally new thing, you get to use a balanced chemical equation to do it. There's no secret, there's no weird conversion. If you're going from moles of one thing to moles of another thing, you have to get the mole ratio from the BCE, okay? I want you to make a note on your chart or someplace else on notes, don't care. The mole ratio from the BCE just means look at coefficients. The couple problems I'm going to do today are going to be so valuable for your homework and for trying to get through some of these other things. So make sure you're taking good notes today. Okay, so when we're looking at the coefficients, that's after it's balanced. So before we even start a problem, what do you think we have to establish first about the reaction?
What type of reaction?
Okay, what type of reaction? We have to predict the products, and then we have to balance it. That's before we even start with math. Okay, so we're going to always start with BCE and then kind of go from there. But once you get to moles of that one thing and get to moles of that other thing by using your coefficients, then you can get to anything else for moles. I can ask easily for you to find grams of the product made, or particles of the product made, or volume of the product made. It's easy to go back and forth when you have this bridge. The bridge is the coefficients from the BCE. Yeah.
So how is this different than the equations that we were already doing?
Because in the equations you're already doing, we're just talking about one substance. You're like grams of carbon dioxide to atoms of carbon dioxide.
Oh, so
or
now we're
molecules.
switching from like carbon dioxide to oxygen.
Yeah, something different. And that writing the identities here, like carbon dioxide, oxygen, whatever we're writing, is very important, because then you'll like, what was I writing? What was I talking about in the problem? It's good to write them down. Okay, so I'm gonna start you off with my favorite type of example. Cupcakes. Woo. Okay.
Yes.
So here we go. I didn't bring you cupcakes today, but maybe I will in the future. All right. So I'm on that low teacher salary. All right. So cupcakes use baking soda to make them rise so they're light and fluffy. The reaction this reaction creates small pockets of air in the cupcakes to give them their texture. This is the reaction. What do you notice? Do you recognize this?
Before we did
In number 4 yesterday. Yeah. Yeah, okay, so write down your, I'm gonna put CE. Why am I not putting BCE? It's not balanced. So even before I finish reading, I want you to write down your BCE and balance it for me. This one is not on your coats at all. The first one's not. This one's gonna be one big example. I want you to write down the CE, and then I want you to balance it to make it BCE. And then tell me what you're writing. So what are my numbers here? To where? Sodium bicarbonate, aka baking soda. Yeah, and in front of the carbon dioxide. Good. Okay, that good? 2 sodiums, 2 hydrogens, 2 carbons, and 6. 1 plus 1 plus 4. 6 oxygens. Whew. Step 1 done, baby. All right. So we have this cupcake. I need to make, so I'm an avid baker. Used to work at a catering service. I don't have time to bake anymore, but I want to make the perfect cupcakes for you when I do bring them. So I need to make sure I have just the right amount of carbon dioxide per cupcake. That exact amount is 50 milliliters of carbon dioxide per cupcake to make just the right amount of lift. What mass of baking soda should I use per cupcake to make this much gas in SPP? So before we start, we've got a BC. Now this nonsense here about me baking is useless. We need the given. What is the one piece of given information? Write that down. So the step 2 here is look for your given, and then look for your unknown. My unknown is my question. No, not quite. It's going to be a quantity I can calculate. Mass of baking soda. What is mass units? Grams. And what is baking soda? NaHCO3. All right, I'm going to write that better down here because I can't fit what I need to here. So my given, I'm going to start with here. So you always start with your given because you can't start with a question, right? So the given is 50 milliliters. Let's put 50.0 because I meant to put 50.0 there. Milliliters of what? CO2. Okay, so before I move any further, I'm just going to remind myself my grams of NaHCO3 are what I'm looking for. All right, so how do I can't do anything with milliliters. What is the next unit you think we should go to get me to something usable for stoichiometry? Liters, right? So how do I get to liters?
Milliliters on the bottom.
Milliliters on bottom.
Liters on top, and then
1 liter. 1,000, right? The King Henry died by drinking chocolate milk guy. He says there's 1,000 milliliters in a liter. Okay, this is liters of CO2, by the way, CO2. All right, so what unit cancels? Milliliters, yay. All right, so I want to make that perfect cupcake, so I got to do it here. I'm in liters of gas. What comes to mind?
22.
I hear mole, and I hear 22.4 liters. So where does that go here? 22.4 liters goes on bottom of CO2. 1 mole of CO2 goes on top. Okay, so this is a standard old metric system conversion. This is a conversion that we just talked about this morning for mole relationships. Now I'm in moles of CO2. Fantastic. I don't care about CO2 though. What was my question pertaining to? So what identity? Baking soda, right? So this is when I get to use that bridge. What was the bridge? The mole ratio from the BCE now up here. Okay, so my BCE tells me the relationship between carbon dioxide and sodium bicarbonate. What is the relationship? 2 to 2. So for every 2 moles of sodium bicarbonate I use, I create 2 moles of carbon dioxide. So the ratio is 2 moles to 2 moles. So that's exactly what I'm writing here. So the ratio you just said was 2 moles of who goes on bottom? CO2, because I got to cancel that. And what goes on top? So 2 moles of NaHCO3, so sodium bicarbonate. Okay, so I'm almost to the end here. I'm almost to the finish line. What's my last step?
You have to convert it to grams.
Right, convert what to grams?
The moles of baking soda.
So 1 mole of sodium bicarbonate. And how would you figure out the grams? I hear calculators. Yes, how would you figure out grams? Periodic table. Tell me the mass of sodium. 23, okay. Plus 1.008 plus. Let's go, people. 12.01 for carbon plus times. So 16 times 3 has to be appropriated before you add it. So that's 48. So you add that to 48. What do you get? 84.018 grams. Okay, so I just squeeze that in there. That was a long process, but it's not a hard process if you know your relationships, right? Some of us were rattling these off. Some of us were like, this is Spanish. Not sure what's going on. So your relationships, you know. Metric system, 22.4 liters per mole at STP. This is the new one. This is where'd you get this relationship from? The BCE. This was our mole ratio, MBC. And this one, is this new? No, this is molar mass by calculating from the periodic table. Okay, so then on your calculator, calculate what the total grams is. Our total grams are. Yeah.
Isn't 2 to 2 taking 1 to 1?
Yep, I'm just exactly writing what's in the BC though. It calculates to be 1 to 1 though.
Could you take that out?
Yeah, but then if I asked you what the mole ratio was, then it might vary based on the test, but you can put 1 to 1. I understand what you're saying.
So is it, like I haven't answered that. How many things?
Tell me the full answer first, and then we'll
1.18754.
0.1875. I'm gonna stop there for 4 grams of sodium bicarbonate. Okay, and then how many sig figs would you need here? You see how many here? 3. Metric doesn't matter. 2 in this particular measurement. Ratios don't matter. They're not measurements. They're ratios. They're different. And then that's got a ton of sig figs, right? So what's our limiting one? 3 sig figs. So round that. 0.188 grams. Okay, and I'm going to reread the question to you because it actually said this is the amount of CO2 per cupcake. So this actually, 0.188 grams of sodium bicarbonate is present per 1 cupcake. And you don't have to write it like that, but I want you to know that that's how much is present per cupcake to make that perfect amount of liquid. Question?
So, the 2, how would you do it right there in between liters, you know, where it says 2 moles?
How would you calculate?
Would you do times 2 or just
Times 1. Or so what I do is I put 50 times 1 over 1,000 in parentheses, or just divided by 1,000, times 1 over 22.4 in parentheses, or just divided by 22.4, times in parentheses 2 over 2, or just times by 1. Just I just ignore it. It doesn't change it at all.
Okay.
And then times 84.018. Yeah. So we got our answer. All right, who got that? Yeah. Looking at this particular one here had 3 sig figs. That's how we got it. Okay, so that amount of baking soda is required per cupcake. So if I wanted to make one for my class, let's say 24 cupcakes, 2 dozen cupcakes, what would be my total amount I would need? What would you do in your head? By what? 24, right? So when you multiply that by 24, you're actually doing stoichiometry. You do stoichiometry in everyday life all the time. You're like, okay, I need this amount of time per assignment. I've got 5 assignments, so I need X amount of time because you're multiplying it by this. So all you're doing in your head was this amount of baking soda per 1 cupcake, and then what did you say you did? Times 24, specifically 24 cupcakes. Cupcakes. That's exactly what you just did. But then when you multiply it out, what did you guys get? 4.50 grams of sodium bicarbonate. Okay, so if I was a baker, that's exactly how much I would add to my baking stuff. And that's how I would make my cupcakes, right? All right, so now using that amount of baking soda, how much total in all 24 cupcakes, sodium oxide would be produced? So now, you've already got your BC, right? Same BC the whole time. What is your given?
Well, now you know how much sodium or baking soda is in cupcakes.
Right, so what's my given? What number am I starting with?
4.50.
4.50. So it says using that same amount of baking soda. So I already know that. It's just not in the problem, it's right above it. So you got that. So what are you starting with? 0.50 grams of sodium bicarbonate. Okay. And what do I want to get to?
Sodium oxide.
Sodium oxide produced. So what does it mean when it says how much though? What unit is much? Grams is actually asking how much mass is being produced. So question, grams of Na2O. Okay, so we have grams of sodium bicarbonate to start with. What was my first? Grams to moles. I can't do anything except go to moles on this particular one. We already have that molar mass. What was it? 84.018. Thank you. And that helps us cancel grams of sodium bicarbonate with grams of sodium bicarbonate. Now I'm in moles of sodium bicarbonate. Who cares about sodium bicarbonate? Who do we care about? Sodium oxide. So where would you be looking at right now?
BCE.
I'm going from moles to moles, right? Moles to moles, two different things. So I'm going to look at moles to mole ratio. What is my ratio? So this has a 1 here, this has a 2 here. So these two are the ones that you're looking at. 1 mole of sodium oxide is produced for every 2 moles of sodium bicarbonate made or decomposed. So 1 to 2. So that's when you look at your BCE. So what am I writing right here on the bottom?
2 moles.
Baking soda.
So 1.
1 mole of this. And where do we get this from again?
The BCE.
BCE. I'm just going to write that up there so we remember that's where we got it from. Didn't come out of our butts. We got it. Okay. So I'm still into my final unit though. Now what do I need to do? Go back to grams of sodium oxide, in this case, not sodium bicarbonate. So this molar mass is useless. Right. So what goes on bottom?
1 mole.
Na2O. And then how would you get grams of sodium oxide? PTOE. Add it up. What do you guys get? Calculator. I'm asking for full body participation.
62.
62?
62 grams.
Okay. Grams of sodium oxide. So what units cancel? That I've not canceled yet. Moles of bicarbonate. Moles of sodium oxide. I'm only in grams of sodium oxide, which is what I wanted. Yes! The cupcake's going to come out perfectly. Yeah.
What would you get the 2 moles of?
This?
Yeah.
I looked at the BCE and looked for the coefficient. So it says 2 baking sodas for every 1 sodium oxide. You got me?
No, that's what I got.
This right here, this problem pertains to that first BCE you wrote down.
Yeah, but I'm not seeing the coefficient in front of.
There's a 1 there. So that's a 1 and that's a 2. Did you write that down?
Yeah.
So this is the 2 that went with sodium bicarbonate, and this is the 1 that went with sodium oxide. It's just pulling the coefficients down to the ratio. Okay, so what did you guys get here?
1.66.
I'm going to write that over here. 1.66 grams of sodium oxide, and that's in all of the 24 cupcakes, right? So if you had to get to how much is in each cupcake, what would you do? Divided by 24. You'd actually be multiplying by 1 cupcake over, no, we just divide by 24. Anyway, that's important because I don't want to poison you. Sodium oxide is actually somewhat toxic in large amounts, so I wouldn't want to put too much in there because I want you to continue in chemistry with me, right? So that's why this is important. You gotta make sure you gotta know the toxicity of your chemicals too. All right, last one. Tell me what I start with after you read it. Or maybe tell me what your question is and what you start with.
So, given initially, you do the 50 milliliters of CO2.
Right, so given the very initially, you were given 50 liters of carbon dioxide. Okay, and what was my question?
Molecules.
Molecules of what?
CO2.
Oh, look, I'm starting with CO2, and I'm ending with CO2. So what is this? Is this new stuff or is this old stuff? Old stuff. We don't have to have a BCE. We don't have to have a bridge with mole ratios. It's the same old, same old. But what do I do to get rid of this milliliters?
You times it by 5.
So 1 liter of CO2 on top over 1,000 milliliters of CO2 on bottom. Okay, milliliters cancel. I'm in liters of a gas. That's when the 22.4 liters comes into play. 22.4 liters of CO2 come into play. What goes on top?
1 mole.
1 mole. Whew, we got 1 mole. All right, 1 mole can easily get me to molecules. With what? Avogadros. So 1 mole of CO2 on bottom, and what goes on top? 6.022 times 10 to the 23rd molecules of CO2. So this was an easy one because we had no requirement to go anywhere else except for CO2.
Sorry. Did Fernanda come on sitting here?
Who?
Fernanda?
No.
They said our shipment was there.
Okay.
They told me I had to go down the loading dock, and no one's out on the loading dock, so I just
Don't call her.
I'll go back to doing it.
No, go back to your class.
Sorry.
So if we have our liters of carbon dioxide canceling, our moles of carbon dioxide canceling, and we have molecules left. So that's one that I could have put on the quest easily. And then that's like 1.34 times 10 to the 21st molecules. Anybody?
Yes.
Of CO2. Just kind of look that up. Okay. So thinking about what we just went through. We just went through reaction stoichiometry. New concept, but what's really new about it?
Just the BC.
BCE and the ratio that we had to pull from it. So on a scale of 1 to 10, 10 I'm a boss, 5 I'm like almost a boss on this, 1 like what just happened. Okay, throw them up. Let me see. Do you see what we're doing? Okay.
But I was like initially like a 4.
Okay. So we didn't have a lot of growth. Okay, let me go through maybe one more type like this. This one's on yours. Okay. This one is on yours. It's called student lecture practice. You try. Some of them, yeah. Nope, not this one. I'm gonna do the first one for you. I had all kinds of jokes to say about you. All right, find this on your paper, and I want your full participation. Make sure you're writing down these, because if not, when you start your own, you're not gonna know what to do. Okay, just being honest. All right, so this one I'm actually not giving you a cute cupcake scenario. It's just like pure chemistry. Decomposition of potassium chloride. Start me off. KO3. Okay, that's potassium chlorate. If you know your polyatomics, that came quickly. Chlorates break down to, that's carbonates break down to carbon dioxide. Chlorates break down to oxygen, because we don't want to make chlorine because then we die. Okay, so this is going to break down to oxygen and potassium chloride. All right, cool. We got that one. Yay, that's the gummy bear experiment right there. Woo. Okay, so balance?
No.
Okay, balance? Sorry.
2 potassium chlorate.
Uh-huh. Oh, sorry. Yeah, both of those.
Then we can put a 2 the oxygen.
You had 3. Got you. All right, that's done. I got the two handled here. All right, so step 1, read. I'm not writing that. Step 1, BCE. Step 2, givens and unknowns. And then we would start, right? This one right here is just like a pre-question. So tell me what the ratio between potassium chloride and oxygen is. So 2 of these to 3 of these. Where are you getting those random numbers from, people? Coefficients. It's not magic. It's reading the problem. So this would be like 2 moles of KClO3 for every 3 moles of O2. Okay, this is the ratio. This could easily be flipped if we needed to, depending on what our setup is like. All right, so that's kind of like a pre-question question. Let's go to the real question. Yeah, you're good. This is on your paper. It's called You Try Student Practice 1. It is on the lower right-hand quadrant. It's little, but it's there. Okay, so now we're reading the question. Tell me what's important you're writing here. Alex, go stand up at the lab station.
75 grams of potassium chloride.
And what would you call that? That is one of the givens. That is the only given, actually, right? All right, what is my question? So I'm just going to write that over here to the side. Question, grams of oxygen gas. All right, so this one's definitely reaction stoichiometry, because I'm starting with A and I'm going to B. Or I'm starting with one thing and I'm going to another thing. So you know you're going to have to use what?
BCE.
BC for the mole ratio, right? Eventually, we're just not there yet. So I'm gonna put my BC right there. Oh, well, no, I'm gonna hide mine. You guys have your own. What do I do first with grams? Convert it into moles. So what is that process? 1 mole on top, 1 on bottom. So quickly calculate. What's potassium weigh? PTOE, people? 0.1, okay, plus chlorine. And 3 oxygens? 6. So 6 times 3 is 48, right. So what's that mass? 122.55 grams of KClO3. Okay, so this is going to be a process you will do all the time. You got to calculate molar mass. So grams of potassium chlorate, that shows us we're in a good place because now we're in moles of potassium chlorate. Yes, we're in moles of this thing. I want to go to another thing. Moles of oxygen. So how do I do that?
So you put 1 mole of potassium chlorate on the bottom.
Ooh, but where are you getting the numbers from? Yeah, you know your units. You just got to find the numbers. So what number went with potassium chlorate?
Okay, so 2.
2. Okay, so I'm going to put 2 moles of KClO3 on bottom. And oxygen? 3, because the coefficient says 3. So don't make up numbers. You got them in front of you. So the 3 came from BC. And, oops, I've lost it. I'm going to put BCE head up on top of this just to remind you that's there. Okay, so now we're in moles of oxygen. And just refresh your memory, what are we looking for? Mass. So I'm almost there. Yes, grams of oxygen, though, which is a different mass.
So 16 grams of oxygen.
Diatomic, so 32 grams of oxygen on top, 1 mole of oxygen on bottom. So what most people want to try to do is they're like, oh, there's 3 moles of oxygen, I'm going to put a 3 down here. No, you've already accounted for the ratio. Ignore that ratio when you move to your next step, because it's just always per 1 mole of that item, so then you can get the molar mass of 32, not something crazy. Okay, so moles of potassium chloride go away, moles of oxygen go away, we're stuck in grams of oxygen, score, that's what we wanted. Okay, calculate from a chip. 29 point what? 29.3757 grams. I'm stopping there, that's cool. Tell me what to do for sig figs. Where was my sig fig number limiting? I'll put like 0.0 here so you're looking crazy. 3 sig figs at the beginning, so it's probably 3 sig figs at the end here. So round that to 4 grams of oxygen. Yeah. Good question. So a lot of people forget to multiply by 3 and divide by 2. So in your calculator, sometimes if you're, who's a parentheses person who likes to put like all kinds of parentheses? Okay, I would put like 75.0, oops, not grams, 75.0 divided by or times by 1 divided by 122.55 times 3/2. That's how I handle that, because it multiplies it and it divides it at the same time, and then times 32. Or in your calculator, 75.0 divided by 122.55 times 3, and then stop there, divide by 2, and times 32. Either way works. It's that base form. Divide by 2. So I already multiply by 3, then divide by 2, and then times by 32 because it's on top. Okay, so same BC. We got 2 more on this. You guys see them on your paper? What is your given? I'll give you guys a break after this, okay? Thank you for pushing through. Potassium chlorate. All right, what's my question? So question, liters of oxygen. It's nice to write it there because sometimes you'll read paragraphs and you're like, oh, what's the question? Just write it down. All right, I'm in grams. Can't do anything until I get to moles. You're going to start to say this in your sleep. And then call me. I'll treat you. This is, you don't want to be dreaming about this. What's on the bottom? That mass we already calculated. Yes, 122 grams. I hear you. Okay. Okay? Oh, almost. Oh, not quite there. See, that's liters of oxygen gas. This is not a gas.
Oh, so you have to use an internal.
Not quite. I have a reaction. Where's your reaction? You have to use your BC to get from this guy to oxygen. Oxygen. Can't say oxygen right now. So you have to get from here to here. And yeah, because it's a reaction, so that's why it's going to oxygen gas. Okay, so what's that ratio? So 3 moles of oxygen on top, because that's what you told me from the BCE earlier, and 2 moles of potassium chloride on bottom. Same story. Okay, those numbers just straight come from BCE, and I'll write that here just to remind you. And then I'm in now I'm in a place where you can get me to liters. 1 mole on bottom. Yeah. And how do you know that number? Just remember it, right? 22.4 liters per mole. Okay, so then grams of potassium chloride go away, moles of potassium chloride go away, moles of oxygen go away, and we're stuck in liters of oxygen, which is what we wanted. When you're ready. 14.668 liters of oxygen. How many sig figs should that be reported to? 3. So what is it? 14.7 liters. It's making a little bit more sense. One more for you. You're gonna have to go back and look at another question though, because it says in part B. So when you're ready, tell me what the given is. Where are you getting this number? Where are you getting 75 grams from? Part B says to look back at Part B and start with potassium chlorate, and it said to use 75.0 grams of potassium chlorate. And what is our question? So that's KCl, right? Our question is KCl, not KClO3. So we're starting in our grams of potassium chlorate. First step again. So what is it? 1 mole on top, and what goes on bottom? Only the 3rd time we've seen this number. It's kind of nice though, we don't have to recalculate again. So now I'm in moles of potassium chlorate. Give me the moles of something else. You have the BC, right? It's in front of you. Mine's on the other screen. 2 potassium chlorides, because that's what the ratio said in the BC. So again, it's essentially a 1-to-1, but I'm just simply pulling straight from BC, plopping a 2 there, straight from BC, plopping a 2 there.
So when we take from the BC, we're only going to take from the final reaction part of it?
The final coefficients, right? Yep. Okay, I'm so close, guys. Right, so what's going on bottom? Right, so once you're in moles of potassium chloride, it's easy to get to grams through molar mass. And what's that molar mass? This is potassium chloride, not chlorate. 74.55 grams. You just added it up from K plus Cl. And final? Whenever you're ready. 45.66. Almost 6. Just going to stop there. There's our final answer. Okay, so I like the cupcake example better, but I want these are the style questions you be asked on your exam and stuff like this, not in fluffy terms like cupcakes. So if you feel comfortable with this, I want you guys to go ahead and with a partner. If you need to move. Start with question 2 and 3. Okay, you're gonna have to write BCE first, and then go through some math. Practice this. We still have about almost 45 minutes left in class, about 40 actually. So plenty of time to get those 2 questions done. Okay, you see the practice underneath that? Yep. Get up and move. Get some oxygen to your brain. Get some water if you need to. But I want you to practice those so you're happy when you leave.
Practice 2 and 3.
Okay, stay focused for me though, okay? And we'll check, I'll write the answers in the work so you can check yourself as you go, shortly.
Oh, where was it? I don't even know where it came from.
Practice or anything?
I work good with tape. Yeah. I'm not from my tape. Hold on. What are you looking for? I've already taken up some of them. I have them on my iPad, so I'll look later. Right now,
Oh.
this stuff is my file.
They feel like monitoring up by C2 because it's a big 7 2 yields SI. I think that part because it's always mono for
Yeah, I was thinking also.
and then plus yeah. I was just gonna ask her about that one. What is that? This is balance, right? So now that it's not two in front of the carbon.
Yeah? Okay. Yeah, I'm just gonna read it.
But there would still be a 2 in front of the scale. Just like I'm trying to balance it.
I'm not going to see. You also go to C, right?
Yeah, and then you have two C's on one side. Well, you have three C's on one side and 2 on one side.
So then you need to put 3 on that C and then a 2. Excessive carbon.
It says with an excessive carbon.
With a lot of carbon. Like,
So like I don't really need to even worry about it.
I don't know, honestly. There's no like specific number.
So that's irrelevant information right now. Well, this is I like that.
Well, it's part of the big 7.
It's at nitrogen. Let's see, it's 1, 2, 3, 4, 5, 6, 7. 7
Good try.
and then
Screw me up and I was right.
So, I don't know if it's weird. Because I keep saying heat and I think there's something related to like it's fire.
So you get SI substitute to plus C. Then SIC plus AC.
Yeah.
Miss Emma, what if I put some excess of carbon?
Doesn't matter. It doesn't. It's irrelevant.
Oh, the grams and moles.
Yeah.
Hey.
So I thought I understood this, but when I looked at like the first one I like for A when it says it's heated with an S.
Let me talk about that real fast. I'm going to talk about this. Hey guys, if you are confused on A, it's because you're reading too much into it, which is actually hindering you from pulling out the two important pieces. This whole entire time we look for a given and one unknown, one question. So 50 grams of silicon dioxide. Oh, I really thought that highlighter was working. When you look here and you see 50 grams of silicon dioxide, what is that called?
Given.
The given. Write that to start with. Then you're like, blah, 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 blah. How much silicon monocarbide is made? What is that? Grams, silicon monocarbide, so SiC. So question, grams of silicon monocarbide. This other information is just about the experiment. It's just because that's how chemistry is. It's not just in, it's not an unrealistic example. It's a realistic example because it's about an experiment. So don't get confused by the details. Pull out the two pieces that you need, and that's it. Move on from there. It works still. That's good.
Because I right now is huge. Why would you say? We just carbon, we just carbon, mole carbon, mole carbon counts up with mole on top, and mole carbon. I'm sorry, oh yeah, that is the two moles. I'm just gonna count the
One of them here, it looks like always that's why.
it's only gonna be 18.2, it's only gonna be.
Okay, good answer. Really? Okay, I was like, I think the second one is also right. I can't remember. All right, things are so okay.
How many atoms of oxygen will be produced at 4.6 ounces of carbon dioxide? So 4 points? Silicon dioxide. You were going to break the moles down to atoms and then that's one
I think some ways to do it is just we'll see what we get.
That's just
I'm pretty bad as that. I didn't mean that. Have one. How many oxygen? Is the Something is one more. Yeah, the those should be actually. It's the one more oxygen.
See? On my BCEs with So on this one, we're gonna, since it says how many atoms of oxygen were produced, I looked to see where oxygen was produced. It was produced in the form of carbon monoxide. That's why I went there. You can also do an internal mole ratio with silicon dioxide, but I'm doing it the more technically correct way. So when you get to moles of carbon monoxide, your job is to get to something that's smaller, which would be molecules of carbon monoxide. And then in one molecule of carbon dioxide, there's one atom of oxygen. Alright guys, look up here for part C, eyes up here. I want to explain you the reactionally correct way. Some of us are going to do it a different way and it's fine as long as you get the right answer, the same answer. So if you start off with your moles of silicon dioxide and the question says how many atoms of oxygen will be produced, produced means made in a product form. Well, the only place where oxygen is present in product form is in the form of carbon monoxide. So I went directly from silicon dioxide to carbon monoxide with this lovely BC mole ratio, and then I was able to go from carbon monoxide down to the atomic level. So from carbon monoxide I went to just one molecule of it, but you know the ratio is, the mole ratio, the conversion is Avogadro's number of molecules per mole. And then from one molecule of carbon monoxide, I said it only contained one atom of oxygen because of that internal ratio of 1 to 1. So there you should be getting this. Is that what you got when you get your way? Okay. So I'm going to leave that there, but I'm expecting you're starting on number 3 here shortly. And if you're sitting in a group of more than 3, then separate yourselves. 2 people work better to get 2 to 3 people work better than 4 to 5. So if you're working by yourself, work by yourself. So the synthesis what's the synthesis, right? Synthesis is 1 to 1. So aluminum hydroxide gas. If you're sitting with a group of more than 3 people, somebody move. I know. Well, just scooch away. Just two. It's good. Anyway. This just says it doesn't say from. Oh, the question. So. Oh, you just made up. You just thought that like CO. They got 90. Okay. And you're supposed to say model Oh, that is just
Oh wait, no, that's I got yours. I got
for reminding me, but you guys were responsible for. We just did one together. You guys were going to do 3. I'm going to talk in just a couple minutes about what you guys
What? Do you know where it is?
It's the one where we did the wonder.
Oh yeah.
They call it veteran part now. That's why I didn't know.
Wait, are you doing realists today?
No, that's just weird.
How often was it like?
It's the last one, Dawn. Bye. Bye.
I was just saying if you were going to
And then I talk to myself, and then it is still
how did you say
Alright guys, wrap up that problem that you're working on in about a minute. We're going to go over number 4. And then do you know what balances or you want balances for that balances? Would be and also we have to do some more. I'm going to give her 4. That's just like nominal.
so if it has a 3 AL2O3 plus 3H2O2 AL2H. Can you help me out? How many moles of product?
Yeah. But I don't know what kind of functions. What if she needs
As in like 2ALOH3? Was the whole thing on the right side? How many moles of product? So it's like whatever it's in the moles. So we have to
You able to that's 3. We don't know
She's like thinking that
it's just 3. Yeah, because then
You know it though. You know it better than you think. Alright guys, wrap up. I want you to come back up here in 30 seconds. I'll answer questions and you're back up here. 30 seconds. I'm counting in my head. 20. I'm at 20. 10.
Can we put 33.4 on like a chest?
9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, thumbs up if you got this one right. Or something close. Yeah. Second one. Yeah. Okay, let me get it. Number 2? Yeah? Okay. C. We all got right because I had it on the board earlier. Okay. So I'm going to number 4, and I want you to show you something, just the last conversion that I didn't talk about earlier because I wanted you to practice this stuff first. This, who saw in the lab on the bottles like 1M hydrochloric acid, 1M copper 2 sulfate, 1M, who saw those numbers in front, right? Aren't you like curious, like what the heck does that mean?
I learned that fast.
Yeah, you're like, what does that mean? It means something called molarity. Okay, so at the top, someplace on notes on your paper, I'm writing above question 4 because I'm going to do question 4. But big M, capital M, means molarity. Molarity. What unit do you think is involved in that in some way or form? Mole. Who would have thunk? Okay, the actual, like, you know how density has a fractional unit? Like, if I said density, what do you immediately think?
Kilo.
What?
Mass over volume.
Okay, mass over volume is what I was looking for. That's it's good. You weren't reading my mind at the time. So when I say molarity, there's something I automatically think of, and you're getting ready to. It's called mole per liter of solution. Molarity, mole per liter. Molarity, mole per liter. I'm trying to help you there. Okay? I'm really trying. I'm stretching it. You're like, what in the world is she doing? So, occasionally I'll give you a number for this. I will always give you a number for this. So, for example, if I said 2 molar means 2 moles per 1 liter. It's always per 1 liter. It's just the number on top changes. Now, this is really valuable to know whenever I give you 2 givens. I've been giving you 1 given this whole time, right? 2 givens is just because it's an experiment, and a lot of times I'm giving you a concentration of a solution, and I'm giving you like, oh, use 5 milliliters of it, or use 10 milliliters of it. Well, that's 2 givens, so then you're like, where do I start? You start with both of them. So the trick is this. Do you realize this is per liter of solution? This is not a gas. Okay, so you keep the 22.4 liters with gases, you keep molarity stuff with solutions. They're 2 different states of matter. They got 2 different ways to use them. So anytime I give you a volume and a molarity, then what you should do is big M times V, and that's always going to give you moles. Always, if you do it right. So once you get to moles, are you good? You can go anywhere. You can go to the moon and back with moles, right? But once you get to moles, that's what you got to do. All right, that's how you get to moles.
Attention teachers, students are getting out of the 10th grade pre-administration assembly and headed back to class. Also, if you are scheduled for detention today, it will be held in the cafeteria. Thank you.
Okay, so knowing what molarity is, I want you to start number 1 with me. I'll write on the BC in just a couple minutes. But go ahead and look at the 2 givens. I give you a 0.01 molar solution, and I give you 120 milliliters. But if I take M times V, what mathematically is actually happening here? What are the units for molarity again? Moles per liter of solution, or I'm just going to put per L. If I multiply it by volume, what unit do you think volume should be in? To cancel. Liters. And that cancels to give you moles. That's why this works, right? It's mathematically same. It's going to work every single time. And then that's why I said once you get to moles, you can go to the moon and back. But this is not in liters. That's what I want you to do first. Convert that to liters for me. In your head.
12,000.
So you're bouncing decimal back 3 places because it's 1,000 different. So it's divided by 1,000. So that's 0.120 liters. And then I want you to multiply that by molarity, but break this into the 2 units. So what am I writing? What goes on top? 0.010 moles on top per, still always, 1 liter of solution. It's always per 1 liter. So then what units cancel? Liters. And tell me how many moles that is. 0.00120 moles. And this was a solution of sodium sulfate. What's sodium sulfate? Na2SO4. Okay. So not a ton different. It's like just a different way to get to moles. But then once you get to moles, you could easily go to wherever you need to in this problem. Okay, so molarity is the last thing I just need to tell you guys about before, because you'll see a couple problems in problem set 12 that say molarity, and I just want to make sure you're prepared. So if I give you molarity, I'm probably going to be giving you liters as well, or milliliters, and then your job is to multiply them together to get to moles. Cool? Okay, so what are you responsible for tonight? You have practice question 2 done, I sure hope. Question 3 hopefully started. You're finishing question 3? Yes? You are finishing question 4.
Yes.
That's exactly what I want to see done tomorrow. I want you to start on problem set 12, but that's something that'll be due later this week. Okay? Also, my goal is to get a s'more geometry lab done this week, but I need some ingredients. So if we can get that done this week, I depend on you bringing stuff in. If that doesn't happen, we'll try to do it next week, but that's not a promise. All right? I'm still doing it.
Yeah.
What ingredients do we need?
Marshmallows.
Yeah. For s'mores? No. Be creative. It doesn't matter.
Wait, is this like a really long lab or like it doesn't take long? So could this be like a half day, like get out of here?
I have to let you know because it's supposed to be before that.
That's a good idea.
Bring stuff in.
That's what I'm waiting on.
That's what I'm waiting on.
I have work. I always have work.